Hello, my name is Jeff Davis, and this is a presentation for underlying regulatory and nail marking on oriented strand board. The presentation will begin with the project charter. The purpose of this presentation is to add under-the-line regulatory marking and nail marking to the existing marking system provided by Matthews Marking. The description of this system will be for APA regulatory marking, producing a 5-inch mark from a 5-inch logo plate, and will also have predefined 1-inch marking locations across the web of the OSB to determine the nail marking pattern. And this system will be manufactured in the same manner as the existing marking system for underline marks. The objective of this charter is to design, manufacture, and commission underline marking system in 10 to 12 weeks from design approval and under a budget of $25,000. The success criteria will make this underline marking system printing the correct nail pattern and passable APA logos on the OSB. This will be defined by the predetermined specifications presented by the customer. The funding of this system are the $25,000 for the underline marking system. This is in addition to the existing $265,000 system that was commissioned in 2007. The major deliverables include the design, manufacturing, and delivery of the system. The installation will be completed by local mechanical contractors, but the commissioning will be performed by Matthews, and the training will also be performed by Matthews. The acceptance criteria for this system include the under-the-line marking system to be a bolt-on addition to the existing system, and the markings to be validated by quality control on site when the system is commissioned. The milestone schedule will be discussed at the end of this project charter. This will include both an estimated timeline and later a detailed timeline of the presentation. The key assumptions for this system are the design to be in a similar fashion to the existing marking system and to use the existing marking system printheads. The constraints for this system include that this new underline marking system must be located in the same existing marking system location. This will be placed on the conveyor, and when the system is not in operation, there must be a sliding mechanism that must not travel past the catwalk for the operators. And finally, for the project charter, the risks. The main risk is the final location being in Canada, which will present a risk for the customs shipment if there are any delays in the transportation from the United States of America over the Canadian border. As stated previously, the project schedule can be seen below in the graphic table. This displays the week 1 through 12 for the concept approval drawings, detailed engineering, production, system test, shipment, installation, commissioning, and the available tech support for the system. The quality control plan is to include that the under-the-line OSB marking system will follow these specifications. The paint is required to be safety blue per OSHA 1910.145F. The marking size must adhere to the 5-inch regulatory APA marking for the APA trademark standards, and the mechanical ANSI fasteners for B18 to 135N. These standards will match all the previous standards for the override system. This is a graphical representation of the work breakdown structure, also known as the WBS. This shows the under-the-line OSB marking as the level 0, and level 1 shows the main phases. Level 2 shows sub-phases in these tasks, and level 3 finally shows detailed requirements that go through these phases. This displays the specifics of the project and shows that all aspects were considered to go into the final timeline. The responsibility assignment matrix shows a tabular view of the previously displayed work breakdown structure. This view shows each phase in the work breakdown structure and also the primary and secondary responsible people. This shows the breakdown of the employees and who will be responsible for each part of the detailed assembly. The network diagram shows each phase of the work breakdown structure, with the critical path highlighted in red. This can be seen to branch off, both through the bottom of the system testing from production, and through the purchasing of components after the detailed engineering. Finally ending with the system test to shipment of the product and then installation and commissioning. The project schedule is detailed in the Gantt chart below. This again shows each part of the work breakdown structure, along with the people responsible for it. Most notably are the bar graphs on the right side of the page, which display the timeline expected for each phase of this project. The resource usage sheet shows a graphical and tabular representation of each person involved in the project and the hours allocated. These are the estimated hours, as the actual work has not yet been completed. This table represents the estimated costs for each phase in the work breakdown structure. Again, on the task name column, you can see each phase in the work breakdown structure, followed by the responsible parties. The next few columns display the work days, rate per hour, the labor rate per day, the labor cost total, the material costs associated, and the total costs on the right. As you can see, the labor represents $22,376 of this project, while the material is relatively cheap at $16.50. This adds up to the total cost of $23,866, which is below the expected $25,000 budgetary proposal. The last table to be displayed is the risk register. This shows the potential risks that could impact this project. The impact, the likelihood of occurrence, the degree of impact, the actions on triggers, the responsibilities, and the response plan. As you can see, some of these are likely and some of these are unlikely, according to the likelihood of occurrence. And you can also see the degree of impact they have. To go down this list, the additional scope requested by the customer during concept approval drawings is a low likelihood of occurrence but will have a high degree of impact. This would include changes in scope to the expected design. Going down the list, the detailed engineering displays concepts will not work or require additional materials. This also has a low likelihood of occurrence, but a medium impact on the project. Next would be delays in purchasing materials arriving. As you can see, this has a medium likelihood of occurrence and a high degree of impact. To follow this row, the actions on triggers would be expediting the procurement, and the response plan would be to immediately contact the vendor and request the expedite, and offer an expedite fee if required. As any big company knows, this is a common problem, but can be alleviated through the use of staying on top and having expedite fees available if necessary. Next will be receiving incorrect materials. This has a low likelihood of occurrence. This has happened in the past. One of the ways to get around this would be to have the vendor expedite new material as their mistake, so they should fix it quickly. Next would be additional materials required for machining. This has a low likelihood of occurrence and also a low impact. Due to the on-site machine shop, we're able to effectively and quickly deal with any issues when requiring extra machining for materials. Next would be missing components during the system testing. Again, this has a low impact, but is slightly more likely than requiring more materials for machining. This is also able to be handled as we hold inventory on site and we have safety stock of all the standard equipment. Next would be the shipping lead time extended due to natural disaster. This has both a low likelihood of occurrence and a low degree of impact, as the customer is unlikely to be able to accept this system shipment if they are in a natural disaster. And finally, integration issues during the installation and commissioning. While this has a low likelihood of occurrence, this would have a very high degree of impact. The action on this trigger would be for Tom to ID the discrepancies with myself and the customer, and we would be able to work through any issues. The response plan would be to have immediate modification of conveyors, if that is the only issue, and then additional design and modifications of the underlying marking system. In conclusion, the proposed underlying marking system will add significant value at a fraction of the initial system cost. The underlying system will be scheduled to coincide with the existing planned shutdown for installation, and there will be minimal extra training for operators as they are currently familiar with a similar system.